Hello, friends. Welcome back to Sleepy Science, where we explore the gentle mysteries of our universe together. Tonight, we're going to unravel a cosmic connection that has puzzled scientists for over 170 years. A connection between the fury of our sun and the trembling of solid ground beneath our feet. Imagine this. It's 1853, and a Swiss astronomer named Rudolf Wolf sits at his desk, surrounded by decades of astronomical records. He's tracking sunspots, those dark magnetic storms swirling across the sun's surface, when he notices something impossible. The same years when sunspots rage most violently are the same years when Earth's crust seems to shudder with unusual frequency. Could our distant star, 93 million miles away, somehow reach across the void of space and shake the very ground we stand on? Most scientists laughed at the idea, but Wolf couldn't shake the feeling that he'd stumbled upon something profound, a cosmic whisper that humanity had been too distracted to hear. If you're enjoying this journey into the beautiful mysteries of science, I'd be so grateful if you'd take a moment to like this video and subscribe to Sleepy Science. Your support helps us keep exploring these cosmic stories together, and it means the world to me. Thank you. Let's begin at the beginning, in that year of 1853, when Rudolf Wolf made his curious observation. Wolf wasn't just any astronomer, he was one of the finest solar observers of his generation. A man who spent decades meticulously counting and cataloging sunspots, he had discovered the 11-year solar cycle, showing that the sun's activity waxes and wanes with predictable rhythm. But his observation about earthquakes was met with skepticism, even ridicule. How could the sun so impossibly far away influence the solid rock of Earth's crust? The idea seemed to violate everything scientists understood about how the world worked. Yet, Wolf wasn't alone in his suspicions. Throughout history, different cultures had noticed connections between celestial events and earthly upheavals. Ancient Chinese astronomers recorded correlations between unusual solar phenomena and seismic disturbances. Japanese observers noted that certain patterns in the heavens seemed to precede earthquakes. These weren't superstitions, they were careful observations by people who watch the sky with the same intensity we bring to modern science. But without instruments to measure what couldn't be seen, without satellites to track invisible forces, these observers couldn't prove their intuitions were anything more than coincidence. The real story begins to unfold when we look at two remarkable periods in solar history, the Maunder Minimum and the Dalton Minimum. These weren't just quiet times on the sun, they were grand solar minima, decades-long periods when the sun seemed to fall into a deep slumber. The Maunder Minimum stretched from 1645 to 1720, 75 years, when sunspots almost completely vanished from the sun's surface. Europe shivered through what historians call the Little Ice Age. Rivers froze solid, crops failed. But here's what makes seismologists take notice during those same 75 years. Historical earthquake records from around the world show a dramatic decrease in major seismic events. Then came the Dalton Minimum from 1790 to 1820, another 30-year period of unusual solar quietude. And again, the pattern held. Earthquakes didn't stop Earth's tectonic plates never truly rest, but the frequency of major quakes noticeably declined. When the sun stirred back to life after 1820, seismic activity seemed to awaken with it, gradually synchronizing with the solar cycle in ways that couldn't be easily dismissed as random chance. Think about what this means for a moment. We're talking about correlations that span centuries, patterns that persist across different continents and tectonic environments. This isn't one scientist seeing patterns in a handful of earthquakes. This is a signal emerging from the noise of 400 years of human record keeping. But here's where we need to be careful, and this is crucial. One of the most common mistakes people make when hearing about this research is confusing correlation with astrology. Let me be absolutely clear, what we're discussing has nothing to do with horoscopes or mystical influences. We're talking about measurable physical phenomena, charged particles, electromagnetic fields, mechanical stress. The connection between solar activity and earthquakes, if it exists, operates through the laws of physics, not through cosmic destiny. This distinction matters because it's the difference between science and pseudoscience, between testable hypotheses and unfalsifiable beliefs. In the 1960s, Soviet researchers began taking Wolf's observations seriously. They were living through the space age, a time when humanity was beginning to understand that space wasn't empty at all. It was filled with particles, fields, and forces we'd never detected before. Scientists like Sobolev and Demmin started investigating how electromagnetic phenomena in Earth's crust might be influenced by external factors. They proposed mechanisms involving telluric currents, massive rivers of electricity flowing through the ground that could be affected by changes in the space environment around Earth. What emerged from this era was a fascinating scientific controversy. On one side stood researchers who believed they could see patterns in the data correlations that seemed too strong to be coincidental. They pointed to statistical analyses, to historical records, to theoretical mechanisms that made physical sense. On the other side stood skeptics who argued that earthquakes are chaotic, that looking for patterns in random events will always yield false positives, that the Earth's crust operates according to its own internal dynamics, with no need for external triggers. This debate raged for decades, and in many ways it continues today. But here's what makes it so valuable. This is how science works. Real science isn't about certainty. It's about careful observation, rigorous testing, and honest disagreement. When scientists argue about whether the sun can trigger earthquakes, they're not being stubborn or difficult. They're doing exactly what they should do, demanding evidence, questioning assumptions, refusing to accept claims just because they seem interesting or profound. The lesson from these early observations is profound. Pattern recognition is one of humanity's greatest gifts. It's how we survived as a species, how we learn to predict seasons and hunt game and avoid danger. But pattern recognition is also dangerous because our brains are so good at finding patterns that we sometimes see them where they don't exist. The challenge in science is to distinguish real patterns from illusions, to find the signal hidden in the noise. Rudolf Wolff saw a pattern in 1853. The question that would haunt researchers for the next 170 years was simple. Was the pattern real? By the late 20th century, scientists had tools Wolff couldn't have imagined. They had satellites orbiting between Earth and Sun, constantly monitoring the solar wind. They had seismometers covering the entire planet, detecting every tremor of Earth's crust. They had computers capable of analyzing millions of data points, searching for correlations with unprecedented precision. The stage was set for someone to finally answer Wolff's question. But getting that answer would require more than just technology. It would require rethinking our assumptions about how Earth and Sun interact, about the invisible forces connecting our planet to its star. Have you ever wondered if the ground beneath your feet is truly as solid as it seems? Or if perhaps we live on a world more responsive to cosmic rhythms than we ever imagined? These are the questions that drove researchers forward, questions that would eventually lead to discoveries that stunned even the skeptics. What those early astronomers like Wolff had glimpsed was just the beginning of the story. To understand how the sun might shake the Earth, we need to understand what the sun is actually doing, what weapons it wields, what forces it commands, what invisible influences it casts across the solar system, like a net woven from light and magnetism and particles moving at speeds that boggle the mind. And that understanding begins with recognizing that our sun is not the calm, steady lamp we imagine when we think of it warming our faces on a spring afternoon. Our sun is violent, tempestuous, constantly hurling pieces of itself into space in storms that could devastate our entire technological civilization if they struck at just the wrong moment. Every second, our sun loses 4 million tons of itself. Not slowly, not gently, but in a continuous explosive conversion of mass into energy that has been raging for 4.5 billion years. And every second, a tiny fraction of that destruction becomes a weapon, a stream of particles moving at speeds up to 500 miles per second, blasting outward in all directions, creating an invisible river that fills the entire solar system. This is the solar wind. And right now, as you listen to these words, billions upon billions of charged particles from the sun are slamming into Earth's magnetic field at supersonic speed. Most people live their entire lives without knowing this cosmic bombardment is happening, but our planet knows. And as we're about to discover, the ground beneath our feet might be responding to this assault in ways we're only beginning to understand. If this exploration of cosmic forces resonates with you, I'd love it if you'd like this video and subscribe to our channel. It helps us continue creating these science stories, and I'm so grateful for your companionship on this journey through the universe's mysteries. Let's begin by understanding what the sun truly is beneath its brilliant surface. When you look up at the sun, and please never look directly at it, you're seeing what astronomers call the photosphere, a seething ocean of plasma at 10,000 degrees Fahrenheit. But that's just the surface. Below lies the convection zone, where enormous currents of superheated gas churn and twist, generating magnetic fields of unimaginable power. These magnetic fields don't stay confined. They burst through the photosphere like twisted ropes of force, creating structures thousands of miles across. Where these magnetic ropes emerge and re-enter the sun's surface, we see sunspots' dark regions that appear dim, only because they're slightly cooler than their surroundings, though still hot enough to vaporize any known material instantly. But here's what makes sunspots matter. For our story, they're not just dark patches. They're windows into the sun's magnetic fury markers of regions, where the star's internal dynamo is generating fields thousands of times stronger than Earth's entire magnetic field. And these regions are where the sun builds up energy for its most violent releases. The sun operates on an 11-year cycle, a rhythm that was discovered through careful observation of sunspots over decades. During solar minimum, the sun's surface is relatively calm. Sunspots are rare, sometimes absent for days or weeks. The solar wind still flows, but it's relatively steady, predictable, almost gentle. Then gradually, the sun awakens. Sunspots appear with increasing frequency clustering near the solar equator. The magnetic fields grow more tangled, more intense. And then sometimes, without warning, the sun unleashes hell. Coronal mass ejections, CMEs. These are the sun's ultimate weapons, and they're almost incomprehensibly powerful. Imagine this: 1 billion tons of plasma superheated gas loaded with magnetic fields and charged particles suddenly erupts from the sun's corona and hurtles into space at speeds that can reach several million miles per hour. A single CME carries the energy of billions of nuclear bombs. And when one is aimed directly at Earth, traveling across 93 million miles of space, it carries with it the potential to fundamentally alter our planet's electromagnetic environment. But here's a crucial distinction that causes a lot of confusion, and it's important we get this right. Solar flares and coronal mass ejections are not the same thing. This is one of the most common mistakes even scientifically literate people make. Solar flares are intense bursts of radiation, X-rays, ultraviolet light, radio waves that travel at the speed of light and reach Earth in about 8 minutes. They can disrupt radio communications and create beautiful auroras, but they're essentially electromagnetic phenomena. Coronal mass ejections, on the other hand, involve actual matter being hurled into space. They take 1 to 3 days to reach Earth, but when they arrive, they bring magnetic fields and billions upon billions of charged particles that can fundamentally reshape our planet's electromagnetic environment for hours or days. Now, between these dramatic eruptions, the solar wind flows constantly like a stellar breath exhaled across the solar system. This wind is composed primarily of electrons and protons, the fundamental building blocks of atoms stripped of their neutral clothing and sent racing outward from the sun. At Earth's orbit, the solar wind typically contains about 5 to 10 protons per cubic centimeter. That might not sound like much. It's a near-perfect vacuum by Earth standards. But remember, this wind fills an enormous volume of space and it's moving fast. Very fast. The speed matters because it determines the wind's pressure, its ability to push against obstacles. During solar minimum, the wind might flow at around 300 kilometers per second. Still incredibly fast, but relatively steady. During solar maximum, especially after a CME, speeds can exceed 800 kilometers per second. That's nearly 2 million miles per hour. At those speeds, even individual protons carry significant momentum and energy. This is where the SOHO satellite enters our story. The Solar and Heliospheric Observatory SOHO was launched in 1995 as a joint mission between NASA and the European Space Agency. Its position is crucial to understanding its role. SOHO doesn't orbit Earth. Instead, it sits at what astronomers call the L1 Lagrange point, a gravitationally stable location, about 900,000 miles from Earth, directly between our planet and the Sun. From this vantage point, SOHO can continuously monitor the solar wind before it reaches Earth, giving us advance warning of dangerous space weather. As SOHO carries instruments that can count protons, measure their speed, and track their density, how many protons are flowing past each second. And it's been doing this continuously for nearly 3 decades now, building up an extraordinary database of solar wind variations. When researchers wanted to test whether solar activity influences earthquakes, SOHO's data became their Rosetta Stone. But let's be specific about what changes during different phases of solar activity, because the details matter. During solar minimum, the solar wind flows more uniformly. The pressure it exerts on Earth's magnetosphere, the magnetic bubble that surrounds our planet, is relatively constant. This pressure is real and measurable. It compresses the magnetosphere on the day side of Earth, squashing it from its natural spherical shape into something more like a teardrop, with a long tail streaming away from the sun. At solar maximum, everything intensifies. Not only does the average speed of the solar wind increase, but the variation in that speed becomes dramatic. One day might see relatively calm conditions. The next day after a CME arrival, proton densities might spike to 50 or 100 particles per cubic centimeter, 10 times the normal level, and speeds might jump to 800 kilometers per second. The pressure on the magnetosphere can increase by a factor of 5 or 10, compressing it significantly. Here's where the numbers become vivid during quiet times. The magnetosphere extends about 10 Earth radii, that's about 40,000 miles on the sunward side. During intense solar storms, it can be compressed to just 6 Earth radii, about 24,000 miles. The magnetosphere is being squeezed like a balloon in a fist. And this compression happens in hours, sometimes in less than an hour. The entire electromagnetic environment around our planet shifts dramatically and rapidly. Now, you might wonder, what does any of this have to do with earthquakes? The connection isn't obvious at first. After all, the magnetosphere is hundreds of miles above Earth's surface. It's in space. How could changes up there affect solid rock down here? The answer involves something called electromagnetic coupling. The way changes in electromagnetic fields in one region can induce effects in another region, even if they're separated by what seems like a barrier. When the solar wind slams into the magnetosphere, it doesn't just compress the magnetic field. It also generates enormous electrical currents in the ionosphere, a layer of Earth's atmosphere from about 50 to 600 kilometers above the surface, where ultraviolet radiation from the sun has stripped electrons from atoms, creating a sea of charged particles. These ionospheric currents in turn induce currents in the ground below through a principle called electromagnetic induction, the same principle that allows transformers to work and wireless charging to happen. But we're not talking about small currents here. During major geomagnetic storms, currents of millions of amperes can flow through the upper layers of Earth's crust, following paths of least resistance through rock and fault zones. Let me give you a concrete example of just how powerful these space weather events can be. On March 13, 1989, a massive coronal mass ejection struck Earth's magnetosphere. The impact was so violent that auroras were seen as far south as Texas and Florida. But the real damage happened in Quebec, Canada. The electromagnetic storm induced electrical currents in the ground, so powerful that they overloaded transformers in Quebec's power grid. Circuit breakers failed in sequence like dominoes falling. Within 90 seconds, the entire province lost power. 6 million people were plunged into darkness. Some areas remained without electricity for 9 hours. The economic cost exceeded billions of dollars, and all because of particles from the sun creating electromagnetic effects that propagated all the way down to ground level. This wasn't a freak occurrence. In 1859, the largest recorded geomagnetic storm in history, the Carrington event, named after the astronomer who observed the solar flare that preceded it, induced currents so powerful that telegraph systems around the world failed. Telegraph operators received electrical shocks. Papers caught fire from the current surges. And in 1921, another major storm disabled telegraph systems across the Northern Hemisphere and set fire to the central station of the New York Central Railroad. These historical events prove beyond doubt that solar activity can reach down and affect Earth's surface through electromagnetic effects. The question that researchers began asking was more subtle. If solar storms can induce powerful currents in the ground, could those currents affect geological processes? Could they perhaps provide the final trigger for earthquakes that were already close to breaking? There's one more piece we need to understand before we can answer that question. The piezoelectric effect and its lesser-known cousin, the reverse piezoelectric effect. Piezoelectricity was discovered in 1880 by Pierre and Jacques Curie, who found that certain crystals, particularly quartz, generate an electrical voltage when you squeeze them mechanically. This isn't magic. It's a consequence of how the crystal lattice deforms under pressure, shifting the positions of charged particles within the crystal and creating a voltage difference. The reverse piezoelectric effect works in the opposite direction. Apply an electrical voltage to a quartz crystal, and it will physically deform, changing its shape slightly. Again, this is measurable, repeatable, and well understood. It's used in everything from watches to sonar to atomic force microscopes. Now, here's the crucial fact. Earth's crust contains enormous amounts of quartz. Granite, one of the most common rocks in the continental crust, is roughly 25% quartz. Sandstone can be nearly pure quartz. Quartz veins run through fault zones. In other words, Earth's crust is filled with natural piezoelectric material just sitting there, waiting to respond to electrical currents. Do you see where this is leading? If solar activity can induce electrical currents in the ground, and if those currents flow through quartz-rich rock, then the reverse piezoelectric effect could convert those electrical currents into mechanical stress, actual physical pushing and squeezing of rock for a fault zone already loaded with tectonic stress, already on the verge of rupture. Could this tiny additional stress be the final trigger that sends it over the edge? This is the mechanism that some researchers propose as the link between solar activity and earthquakes. It's not that the sun is causing earthquakes, tectonic forces are doing that, building up stress over years and decades as plates grind against each other. But the sun might be providing the final nudge, the last straw, the tiny push that determines when an earthquake that was already inevitable actually happens. Before we explore whether this mechanism is actually working in the real world, we need to understand Earth's protective shield in more detail. The magnetosphere and ionosphere, the electromagnetic layers that stand between the solar wind and the surface we live on. Because it's in these layers and the complex interplay between solar particles and Earth's magnetic field that the story of sun-earthquake connections truly unfolds. Right now, invisible and unfelt, you are standing inside one of the most powerful force fields in the solar system. It extends tens of thousands of miles into space, strong enough to deflect particle streams traveling at nearly 2 million miles per hour. dynamic enough to reshape itself in response to cosmic assaults that would otherwise strip away our atmosphere and sterilize the surface of all life. This force field Earth's magnetosphere is the only reason you can stand under open sky without being bombarded by lethal radiation. But here's what makes it remarkable for our investigation. This protective shield isn't rigid. It breathes, it pulses, it flexes and compresses and stretches in response to the solar wind like a living membrane between Earth and space. And every time it moves, every time it responds to a surge of particles from the sun, it sends ripples of electromagnetic energy cascading down through the atmosphere, through the ionosphere, all the way to the ground beneath your feet. If you're finding this journey through Earth's electromagnetic architecture as fascinating as I do, I'd be deeply grateful if you'd take a moment to like this video and subscribe. Your support makes these explorations possible, and I truly appreciate you being here. Let's start with Earth's magnetosphere itself, because understanding its structure is essential to understanding how solar activity might reach down and touch the surface. The magnetosphere exists because Earth is essentially a giant magnet. Deep in our planet's core, about 1/800 miles beneath the surface, liquid iron churns in enormous convection currents driven by heat from the core and by Earth's rotation. This moving electrically conductive fluid generates a magnetic field through a process called the dynamo effect, the same process that makes the sun magnetic, though, on a much smaller scale. Earth's magnetic field emerges from the south magnetic pole, loops through space in great arcing field lines, and returns to the north magnetic pole. If Earth were alone in space with no solar wind, these field lines would extend symmetrically in all directions, forming a nearly perfect dipole field, shaped like the field around a simple bar magnet. But Earth isn't alone. The solar wind, that constant stream of charged particles flowing outward from the sun, pushes against the magnetic field, compressing it on the day side and stretching it into a long tail on the night side. The result is a structure that looks remarkably like a teardrop or a comet. On the sunward side, the magnetosphere is compressed to a distance of about 6 to 10 Earth radii, depending on the intensity of the solar wind. On the night side, the magnetotail stretches out for hundreds of Earth radii, millions of miles into space far beyond the moon's orbit. Within this structure, Earth's magnetic field traps charged particles, mostly protons and electrons, creating radiation belts called the Van Allen belts, discovered in 1958 by America's first satellite explorer 1. But here's where the dynamics become crucial. The boundary between the magnetosphere and the solar wind, called the magnetopause, is not a solid barrier. It's a boundary layer where Earth's magnetic field pushes back against the pressure of the solar wind with exactly enough force to balance that pressure. When the solar wind pressure increases when a coronal mass ejection arrives, or when the solar wind speed suddenly jumps, the magnetopause moves inward. The entire magnetosphere compresses like a balloon being squeezed. When the pressure decreases, the magnetosphere expands again. These compressions and expansions don't happen gradually. They can occur in minutes. Imagine in the span of half an hour, the outer boundary of Earth's protective magnetic field might move inward by 10,000 miles or more. This is a violent dynamic process, and it has consequences that cascade through the entire system. The first consequence occurs in the ionosphere. The ionosphere is not a discrete layer, but rather a region of Earth's atmosphere, extending from about 50 kilometers to 600 kilometers altitude, where ultraviolet radiation from the sun has enough energy to strip electrons from atoms, creating a sea of ions and free electrons. This makes the ionosphere electrically conductive, not perfectly so, but conductive enough that electrical currents can flow through it relatively easily. When the magnetosphere compresses, it doesn't just move the magnetopause. It also squeezes and deforms the magnetic field lines that thread through the ionosphere. These field lines are connected to the ionosphere, they're anchored there in a sense. So when they move, they drag the ionized gas with them. This creates currents in the ionosphere called electrojet. currents, rivers of electricity flowing at altitudes of 100 to 120 kilometers, carrying millions of amperes during major geomagnetic storms. The most famous of these currents is the auroral electrojet, which flows along the auroral oval, the ring-shaped region around Earth's magnetic poles where auroras typically occur. During quiet times, this current might carry 100,000 amperes. During major storms, it can exceed 1,000,000 amperes. To put that in perspective, a typical lightning bolt carries about 30,000 amperes for a fraction of a second. The auroral electrojet carries 30 times that much continuously for hours. But there are other current systems as well. The equatorial electrojet flows along the magnetic equator. Ring currents flow in the inner magnetosphere. All of these currents are responses to changes in the magnetosphere driven by solar activity. And here's the key: these currents don't stay confined to the ionosphere. They close through the ground. This is electromagnetic induction in action. And it's one of the most important concepts for understanding the sun-earthquake connection. When electrical current flows through the ionosphere, it generates a magnetic field, just as current flowing through a wire generates a magnetic field. This changing magnetic field extends downward through the atmosphere to the ground. And when a changing magnetic field passes through a conductor, like Earth's electrically conductive rocks and soil, it induces electrical currents in that conductor. This is Faraday's law of electromagnetic induction, discovered in 1831 by Michael Faraday, one of the greatest experimental physicists in history. Faraday showed that a changing magnetic field creates an electrical field, which drives currents in any conductor present. The faster the magnetic field changes, the stronger the induced currents. During geomagnetic storms, the magnetic fields at Earth's surface can change rapidly and substantially. Variations of hundreds of nanoteslas per minute are common during major storms. These changing fields induce electrical currents in the ground called telluric currents, or ground-induced currents. These are not small localized effects. Telluric currents can flow for hundreds or thousands of kilometers through the crust, following paths of least resistance through conductive rock layers, fault zones, and underground water. The magnitude of these currents depends on several factors: the rate of change of the magnetic field, the electrical conductivity of the ground, and the geometry of conductive structures. In highly conductive regions, areas with significant groundwater, certain types of rock formations, or mineralized zones, the currents can be substantial. During the March 1989 storm that knocked out Quebec's power grid, ground-induced currents reached hundreds of amperes in some locations, flowing through the Earth itself. Now, here's where we need to talk about the electrical potential difference between the ionosphere and Earth's surface, because this is central to one proposed mechanism for how solar activity might trigger earthquakes. Under normal conditions, there's a voltage difference of about 250,000 to 400,000 volts between the ionosphere and the ground. This might sound enormous, but the current flow is tiny because air is an excellent insulator. Think of it like a capacitor, two conductive plates separated by an insulator with a voltage difference between them. During geomagnetic storms, this voltage difference can change significantly. The solar wind doesn't just compress the magnetosphere. It also alters the electrical coupling between the magnetosphere and ionosphere, which in turn affects the ionosphere ground potential. Some researchers propose that these variations in electrical potential, combined with the induced telluric currents, could generate electrical fields in the crust, strong enough to affect rock through the reverse piezoelectric effect. Let me give you another historical example that demonstrates just how dramatic these electromagnetic effects can be. On September 1st and 2nd, 1859, during what we now call the Carrington event, the most intense geomagnetic storm in recorded history struck Earth. The aurora borealis was seen as far south as the Caribbean. In the Rocky Mountains, gold miners woke up and started preparing breakfast because the aurora was so bright, they thought dawn had arrived at 1 in the morning. Telegraph operators report that they could disconnect their batteries and still send messages powered solely by the currents induced by the storm. Some operators received electrical shocks from their equipment. Telegraph paper caught fire from the current surges. This wasn't just electromagnetic noise. This was massive amounts of electrical energy being coupled from space down to ground level through electromagnetic induction. If telegraph wires could carry enough current to cause fires and shocks, imagine what currents might be flowing through the much larger, more conductive pathways in Earth's crust. But here's a crucial point that often gets missed in discussions of space weather and ground effects. The coupling efficiency varies dramatically with location. This is one of the most important lessons from space weather research, and it's essential for understanding why some regions might be more susceptible to solar triggering of earthquakes than others. The conductivity of Earth's crust is not uniform. Some regions have highly conductive layers, ancient ocean sediments, for instance, or rock formations with high metal content or areas with extensive groundwater. Other regions have very low conductivity, dry crystalline basement rock, for example. The induced current density will be much higher in the conductive regions. This means that two fault zones at the same latitude experiencing the same geomagnetic storm might experience very different levels of induced electrical stress simply because of differences in the local geology. There's also a latitude effect. Geomagnetic storm effects are generally strongest at high latitudes near the auroral zones, because that's where the electrojet currents are most intense and where magnetic field variations are largest. This is why power grids in Canada, Scandinavia, and Alaska are particularly vulnerable to space weather effects. It's also why if solar activity does trigger earthquakes, we might expect to see different patterns at different latitudes. Seasonal variations matter too, and this is something that surprised researchers when they first discovered it. The way Earth's magnetic field is oriented relative to the sun changes with the seasons. During Earth's northern summer, the north magnetic pole is tilted toward the sun. During northern winter, it's tilted away. This affects how efficiently solar wind energy couples into the magnetosphere. Some studies have found that geomagnetic storms produce stronger effects during the equinoxes spring and fall when Earth's magnetic field is oriented perpendicular to the solar wind flow. This creates what's called the Russell-McFerrin effect, a geometric factor that enhances magnetic storm intensity during equinoctial months. If solar activity does influence earthquake triggering, these seasonal variations should show up in the data. Researchers have looked for such patterns, and some have found hints of seasonal modulation in earthquake occurrence, though the effects are subtle and still debated. One of the most common misconceptions about the magnetosphere is that it's a simple static shield, a bubble of magnetic field that just sits there deflecting the solar wind. The reality is far more dynamic and complex. The magnetosphere is constantly in motion, constantly responding to changes in the solar wind, constantly storing and releasing energy. During geomagnetic substorms, explosive releases of energy in the magnetotail that occur every few hours during active periods, millions of amperes of current flow through the magnetosphere-ionosphere system. These currents fluctuate on timescales of minutes, driving rapid changes in the magnetic field at Earth's surface. It's this dynamic, fluctuating nature of the magnetosphere-ionosphere system that makes it plausible that solar activity could have near-surface effects. We're not talking about a steady, constant influence. We're talking about pulses of energy, rapid variations in electromagnetic fields, sudden surges of current through the ground, all driven by the impact of solar wind on Earth's magnetic environment, but demonstrating that these effects are strong enough to trigger earthquakes. That's a different challenge entirely. For that, we need data. We need to look at actual earthquakes and actual solar activity and see if there's a real, statistically significant correlation. We need to examine decades of records, carefully controlling for biases and coincidences, applying rigorous statistical tests to determine whether the patterns we see are real or illusory. That analysis has been done, and what it revealed stunned even the researchers who conducted it, a correlation so strong, so statistically significant, that it forced scientists to reconsider assumptions they had held for decades about what can and cannot influence the timing of earthquakes. The data speaks with a clarity that's difficult to ignore, painting a picture of Earth as a planet far more responsive to its cosmic environment than we ever imagined. In 2020, a team of Italian scientists published a paper that sent shockwaves through the seismological community. After analyzing 20 years of continuous data from space and comparing it with every major earthquake on Earth during that period, they found something that shouldn't exist according to conventional wisdom. The correlation was so strong, so statistically significant, that the probability of it being random chance was less than 1 in 100,000, less than 0.001%. To put that in perspective, that's more certain than most medical studies that change how doctors treat patients, more reliable than most psychological research that shapes our understanding of human behavior. The sun, it seemed, wasn't just a distant lamp illuminating our days. It was actively influencing the very stability of the ground beneath our feet. And now, we had the numbers to prove it. If this deep dive into groundbreaking research speaks to your curiosity about our cosmic connections, please consider liking this video and subscribing to Sleepy Science. Your support helps us bring these important scientific stories to light, and I'm truly grateful for each of you joining this journey. The study was led by Giuseppe Di Natale, Research Director at Italy's National Institute of Geophysics and Volcanology, along with his colleagues Valerio Marchitelli, Pietro Harabaglia, and Claudia Troas. These weren't fringe researchers or amateur enthusiasts. They were established scientists with decades of experience in geophysics and seismology, and they had access to two extraordinary data sets that, when combined, could finally answer the question Rudolf Wolf had posed 167 years earlier. The first data set came from SOHO, the Solar and Heliospheric Observatory satellite we discussed earlier. Since December 1995, SOHO has been continuously monitoring the solar wind from its position at the L1.900,000 miles from Earth. Every minute of every day for more than 2 decades, SOHO's instruments have measured the density and velocity of protons streaming past from the sun. This created an unprecedented record, millions of measurements, capturing every variation in the solar wind, every surge following a coronal mass ejection, every quiet period during solar minimum. The second data set was the ISC GEM Global Instrumental Earthquake Catalog, maintained by the International Seismological Center. This catalog represents one of the most careful compilations of earthquake data ever assembled. It doesn't just list every earthquake, it focuses on events with moment magnitude 5.5 and above, carefully reviewed and quality controlled with precise times and locations. During the 20-year period from 1996 to 2016, this catalog documented thousands of significant earthquakes around the world. What the Italian team did was conceptually simple but computationally demanding. They looked for correlations between changes in solar wind, proton density, and the occurrence of large earthquakes. But they did this with sophisticated statistical methods, carefully accounting for all the ways that chance correlations can appear in data. Here's what they found, and the results are remarkable. There was a clear, statistically significant correlation between increases in proton density and the occurrence of large earthquakes, with a time lag of approximately 24 hours. When the solar wind proton density spiked above certain threshold levels, the rate of major earthquakes increased significantly in the following day. Let me be precise about what this means, because the details matter enormously. The researchers weren't claiming that every earthquake follows a solar wind event, or that every solar wind event triggers an earthquake. That would be absurd. Earthquakes are primarily driven by tectonic forces, the slow grinding of plates that builds up stress over years and decades. What they found was a statistical correlation. When you look at thousands of earthquakes and thousands of solar wind variations, there's a pattern. After high proton density events, earthquakes become more likely than they would be otherwise. The correlation got stronger as they increased the magnitude threshold. For earthquakes above magnitude 5.6, the correlation was clear. For magnitude 6.0 and above, it became even more pronounced. For magnitude 6.5 and higher, the statistical significance was overwhelming. This makes physical sense. Larger earthquakes require larger fault systems with more accumulated stress. And these might be more susceptible to external triggering because they're closer to the point of rupture. The 24-hour time lag is particularly intriguing. It's too long to be a direct electromagnetic effect. Those would happen much more quickly. But it's consistent with a mechanism involving the gradual buildup of stress through induced currents or other electromagnetic effects. Think of it like this: the solar wind surge doesn't immediately break the fault. Instead, it begins a process, perhaps heating rock through induced currents, perhaps generating strain pulses through piezoelectric effects that takes hours to propagate and accumulate until it reaches the threshold where the fault finally ruptures. The researchers tested their findings rigorously. They divided their 20-year data set in half using data from 1996 to 2005 to identify the correlation parameters, then applying those parameters to the second half, 2006 to 2016, to see if the correlation held. It did. This is called cross-validation, and it's one of the most important tests for determining whether a statistical pattern is real or just noise. If you find a pattern in the first half of your data, and that same pattern appears in the second half, it's strong evidence that something real is happening. They also looked at different regions of the world to see if the correlation was global or localized. What they found was fascinating. The correlation was indeed global, but it showed regional variations. Some tectonic regions seemed more responsive to solar wind variations than others. The Pacific Ring of Fire, that vast zone of seismic and volcanic activity circling the Pacific Ocean, showed strong correlations. So, did certain regions of the Arabian Plate and South America? Why would different regions show different responses? There are several possible explanations, and this is where the research gets really interesting. First, there's the matter of local conductivity. As we discussed earlier, regions with high electrical conductivity in the crust will experience stronger induced currents during geomagnetic storms. If the sun earthquake mechanism operates through electromagnetic induction, then geologically conductive regions should be more susceptible. Second, there's the question of stress state. Not all fault zones are equally close to rupture at any given time. The Pacific Ring of Fire is particularly active because multiple plate boundaries converge there, constantly generating stress. Faults in these regions might be more sensitive to small triggers simply because they're already near the breaking point. A fault under low stress wouldn't rupture no matter how much electromagnetic energy you pour into it. But a fault that's 99% of the way to failure might be pushed over the edge by a relatively small additional stress. Third, there might be orientation effects. Earth's magnetic field and the induced currents flow in specific directions. Faults oriented perpendicular to these current flows might experience different stress than faults aligned parallel to them. The electromagnetic coupling might literally depend on the geometry of how fault zones are oriented relative to the induced electromagnetic fields. Now, let's look at some specific examples to make this concrete. On February 27, 2010, a magnitude 8.8 earthquake struck off the coast of Chile, one of the largest earthquakes ever recorded. It ruptured a 500-kilometer section of the Nazca Plate boundary and generated a tsunami that crossed the Pacific. In the days before this earthquake, SOHO data showed a significant increase in solar wind proton density following a coronal mass ejection. The timing matched the pattern the Italian researchers had identified. On March 11, 2011, the Tohoku earthquake struck off the coast of Japan, magnitude 9.1, the most powerful earthquake in Japan's recorded history. This earthquake was so massive that it shifted Earth's axis by about 10 centimeters and shortened the length of the day by 1.8 microseconds through the redistribution of mass. The resulting tsunami devastated Japan's northeast coast and triggered the Fukushima nuclear disaster. When researchers looked back at the solar wind data, they found that this earthquake had also been preceded by elevated proton density in the days before the event. Now, I need to be extremely careful here, and so should you if you discuss this research with others. The Italian team is not claiming that the solar wind caused these earthquakes. The tectonic stress that powered these ruptures had been building for decades or centuries. These were earthquakes that were going to happen regardless of solar activity. What the correlation suggests is that solar wind variations might have influenced when they happened, perhaps advancing the timing by days or weeks, providing the final trigger that pushed already critical fault systems over the edge. This distinction is crucial because it's one of the most common misunderstandings about this research. People hear, the sun triggers earthquakes, and imagine that quiet tectonic zones suddenly rupture because of solar storms. That's not what the data shows. What the data suggests is that for faults already loaded with immense tectonic stress, already on the verge of failure, solar wind variations might act as a trigger, the final straw that determines the precise timing of rupture. Think of it like this. Imagine a boulder balanced on the edge of a cliff, held in place by friction, loaded with gravitational potential energy from having been pushed there by geological forces over centuries. That boulder is going to fall eventually. But what determines the exact moment it falls? Perhaps a gust of wind, perhaps a small vibration from a passing truck, perhaps thermal expansion from the afternoon sun, slightly shifting the rock's contact point. These triggers don't create the potential energy that comes from the boulder being high up, but they might determine when that energy is released. The statistical strength of the correlation is what makes this research so compelling. The probability value, less than 1 in 100,000 of being random chance, is extraordinarily low. In most scientific fields, a probability value of less than 1 in 25% is considered statistically significant. 1 in 101% is considered highly significant. 1 in 100,000, 0. 0.01% is virtually certain. But here's where we need to acknowledge the controversy that erupted after this paper was published, because science doesn't progress through consensus. It progresses through vigorous debate and critical examination of evidence. Not everyone accepted these findings. Skeptical researchers immediately raised important questions about the statistical methods, about possible selection biases in the data, about whether the correlation might be an artifact of how the analysis was conducted. Some critics pointed out that when you have 20 years of continuous data with measurements every day, you have about 7,300 data points. With that many comparisons, some correlations are bound to appear just by chance, even if you're looking at truly random data. This is called the multiple comparisons problem. And it's a serious issue in any study involving large data sets and many statistical tests. Other critics questioned whether the researchers had adequately controlled for the natural clustering of earthquakes. Earthquakes don't occur randomly in time. They tend to cluster with aftershocks, following main shocks sometimes for months or years. If the timing of earthquake clusters happen to align with solar activity patterns just by coincidence, it might create the appearance of correlation where none truly exists. Still, others pointed out that the solar cycle itself has a pattern, the 11-year cycle of activity, and that Earth's seismicity also shows long-term patterns related to stress accumulation in plate boundaries. Could these two cyclic processes occasionally align in ways that create apparent correlations? These are all valid concerns, and they're exactly the kinds of questions that should be asked when evaluating any scientific claim. The Italian research team addressed many of these criticisms in their paper and in follow-up responses, defending their statistical methods and showing that they had controlled for various potential confounding factors. But the debate continues, and that's healthy. Science is not about accepting claims uncritically, it's about demanding evidence, testing alternatives, and maintaining appropriate skepticism, even in the face of striking results. What makes this research particularly important isn't just the correlation itself, it's that it revives serious scientific interest in a question that many researchers had dismissed as settled. For decades, the consensus in seismology was that earthquakes are purely internal phenomena driven by tectonic forces with no significant external influences. This study, with its compelling statistics drawn from 20 years of high-quality data, forced researchers to reconsider that assumption. Have you ever felt certain about something, only to have new evidence force you to question your assumptions? That's exactly the position many seismologists found themselves in after this paper was published, and it's precisely this kind of intellectual humility, the willingness to revise understanding in light of new evidence, that makes science such a powerful way of understanding the world. But statistical correlations alone, no matter how strong, don't tell us how something happens. They only tell us that it does happen. To truly understand whether the sun can trigger earthquakes, we need to understand the physical mechanism, the actual process by which energy from solar wind could translate into mechanical stress in Earth's crust. We need to follow the chain of cause and effect, from protons in space to vibrations in rock, understanding each link and confirming that the proposed mechanism is physically plausible and consistent with everything else we know about how Earth works. Imagine you could watch in perfect detail the journey of a single proton from the surface of the sun to a fault zone deep in California's crust. You'd witness a cascade of transformations so elegant, so interconnected, that it would fundamentally change how you think about Earth's place in the solar system. This proton begins its journey in the chaos of a solar eruption, travels 93 million miles through the void at nearly 2 million miles per hour, collides with Earth's magnetic field in a shower of electromagnetic energy, induces electrical currents that flow through hundreds of miles of rock, and finally, through a quantum mechanical process discovered in crystals, more than a century ago, converts that electrical energy back into mechanical stress. That final stress might be tiny perhaps, just a few kilopascals, but if applied at exactly the right place and time to a fault already trembling on the edge of catastrophic failure, it could be the difference between stability and rupture. This is the mechanism step by step that might connect the fury of the sun to the shaking of the ground. If you're captivated by these cosmic connections unfolding before us, I'd be honored if you'd like this video and subscribe to Sleepy Science. Your support keeps these explorations alive, and I'm grateful to share this journey with you. Let's trace this chain of causation from beginning to end, understanding each link with precision, because the beauty of science lies in how it reveals the hidden machinery of nature. We begin as we must with the solar eruption itself. A coronal mass ejection explodes from the sun's corona, hurling billions of tons of plasma into space. This plasma isn't just hot gas, it's a soup of charged particles, primarily protons and electrons, embedded in twisted magnetic fields that were stored in the sun's atmosphere and suddenly released. This cloud of magnetized plasma expands as it travels through space, spreading out, but maintaining its coherence as a distinct structure. When it reaches Earth typically 1 to 3 days after leaving the sun, it doesn't simply flow around our planet like water around a rock. Instead, it slams into the magnetosphere, and the collision is violent and complex. The interplanetary magnetic field carried by the CME interacts with Earth's magnetic field. If the orientations are aligned properly, particularly if the CME's field points southward opposite to Earth's northward pointing field, something remarkable happens: magnetic reconnection. Magnetic reconnection is one of the most important processes in space physics, yet it remains somewhat mysterious even to researchers who study it. Here's what happens when magnetic field lines with opposite orientations come into contact. They can break and rejoin in new configurations, converting magnetic energy into kinetic energy, the energy of motion. This process accelerates particles to high speeds and allows solar wind plasma to penetrate into regions of Earth's magnetosphere that would normally be shielded. During reconnection events, the pressure on the magnetosphere increases dramatically. The boundary compresses inward. And remember, this isn't a gradual process. The magnetopause can move thousands of miles in less than an hour. This rapid compression sends a pressure pulse through the entire magnetosphere-ionosphere system, like squeezing a balloon and watching the stress propagate through its surface. Now, the energy begins coupling into the ionosphere. The compressed magnetic field lines thread through the ionospheric plasma at altitudes of 100 to 120 kilometers. As these field lines are pushed and twisted by the magnetospheric compression, they drag the ionized particles with them through a process called magnetosphere-ionosphere coupling. This creates the auroral electrojet, that million-ampere current we discussed earlier, flowing along the auroral oval. But here's where the process gets particularly interesting for our earthquake story. These ionospheric currents don't exist in isolation. They're part of a complete electrical circuit that closes through Earth's crust. The current flows in the ionosphere from dawn to dusk along the auroral oval, then returns through the crust from dusk to dawn. This isn't a metaphor or an approximation. It's an actual electrical circuit, spanning from space to ground and back to space again. The mechanism by which current couples from the ionosphere to the ground is electromagnetic induction, and we need to understand this process in detail. As the ionospheric current fluctuates, increasing and decreasing as the geomagnetic storm evolves, it generates a time-varying magnetic field. This changing magnetic field extends downward through the atmosphere to Earth's surface. When this changing magnetic field passes through electrically conductive rock and soil, it induces electrical currents in those materials according to Faraday's law. The magnitude of the induced currents depends on several factors. First, the rate of change of the magnetic field. Faster changes induce stronger currents. During the main phase of a geomagnetic storm, magnetic field variations at Earth's surface can exceed 100 nanoteslas per minute. During extreme storms, variations can reach 500 nanoteslas per minute or more. These might seem like small numbers, but remember, we're talking about magnetic fields changing across the entire planet. Second, the electrical conductivity of the ground matters enormously. Conductivity varies by many orders of magnitude depending on rock type, moisture, content temperature, and the presence of conductive minerals. Sedimentary basins, particularly those with saline groundwater, can be highly conductive. Ancient ocean sediments, metamorphic rock formations, with graphite or other conductive minerals and regions with geothermal activity also show high conductivity. In these regions, the induced currents can be substantial hundreds of amperes flowing through pathways kilometers wide. Dry crystalline rock, on the other hand, is relatively resistive. This creates a natural channeling effect. Induced currents follow paths of least resistance, concentrating in conductive zones and structures. Fault zones are particularly interesting because they often contain fractured rock circulating fluids and mineralization, all factors that increase electrical conductivity. In other words, fault zones naturally become pathways for the induced telluric currents. Now, we come to the heart of the proposed mechanism. How do these electrical currents translate into mechanical stress? This is where quartz enters the story, and the tale of quartz is one of the most fascinating chapters in the history of physics and geology. Quartz silicon dioxide, SiO2, is one of the most abundant minerals in Earth's continental crust. Granite, which forms much of the continent's crystalline basement, typically contains 20 to 30% quartz. Quartzite metamorphosed sandstone can be nearly pure quartz. Quartz veins run through fault zones. Wherever rock has been fractured and fluids have circulated through the fractures, quartz often precipitates from solution, cementing the fractures. In other words, Earth's crust, particularly in fault zones, is saturated with quartz. In 1880, Pierre Curie and his brother Jacques discovered something remarkable about quartz crystals. When you squeeze them, they generate an electrical voltage. They called this the piezoelectric effect, from the Greek word piezein, meaning to squeeze. The effect arises from quartz's crystal structure. Quartz belongs to a class of crystals that lack a center of symmetry. When you compress such a crystal, the positions of positive and negative charges within the crystal shift, slightly relative to each other, creating a net electrical polarization, a voltage difference between opposite faces of the crystal. The magnitude of this effect might surprise you. Squeezing a quartz crystal with a stress of 1 megapascal, roughly 145 pounds per square inch, generates a voltage of about 2.3 millivolts across a centimeter-sized crystal. That might not sound like much, but remember, we're talking about a bulk property of enormous volumes of rock. When tectonic forces compress a cubic kilometer of quartz-bearing rock, the cumulative voltage generated can be substantial. The Curie brothers also discovered something else. The piezoelectric effect works in reverse. Apply a voltage to a quartz crystal, and it deforms mechanically. This is called the converse piezoelectric effect, or inverse piezoelectric effect. And it's what makes quartz crystals useful in everything from watches to ultrasound transducers to atomic force microscopes. The coefficient that describes this inverse effect is measured in picometers per volt. That is how many trillionths of a meter a crystal deforms per volt of applied field. For quartz, the coefficient is about 2.3 picometers per volt per meter. Applied across a large volume of rock subjected to strong electrical fields, this can translate into measurable strain. Now here's the crucial question. Are the electrical fields generated by geomagnetic storms strong enough to produce mechanically significant strain through the inverse piezoelectric effect in quartz-bearing rock? Let's do the calculation because this is where theory meets reality. During a major geomagnetic storm, the induced electric field in the crust can reach values of 1 to 10 volts per kilometer in highly conductive regions. In a fault zone, 10 kilometers deep, this could mean a voltage difference of 10 to 100 volts across the depth of the fault. Applied to quartz-rich rock through the inverse piezoelectric effect, this would generate strain on the order of 10 to 100 nanostrain. That is, the rock would compress or extend by 10 to 100 nanometers per meter of length. Is this significant? At first glance, 100 nanostrain seems tiny. You'd need instruments to measure it. But consider the context. Major earthquakes typically occur when tectonic stress builds up to levels that produce strain of about 0.001 to 0.001. That's 100,000 to 1,000,000 nanostrain. The rock is already stressed to perhaps 95% or 99% of its failure threshold. In that state, an additional 100 nanostrain, 0.001% of the breaking point might actually matter. But there's another mechanism to consider, one that might be even more important: heating through electrical resistance. When electrical current flows through rock, it encounters resistance. This is true of any conductor. Electrons colliding with atoms generate heat through Joule, heating the same process that makes toasters work and light bulbs glow. The amount of heat generated depends on the current density and the resistance. In fault zones where currents concentrate and where resistance can be relatively high in certain rock types, this heating could be significant. Laboratory experiments have shown that heating rock by just a few degrees can measurably reduce its shear strength, the resistance to sliding along a fault surface. This happens because thermal expansion creates additional stress, because increased temperature enhances chemical reactions that weaken mineral contacts, and because heating can affect the properties of fluids trapped in rock pores. A research team in the 1980s, led by Soviet physicist Gennady Sobolev, proposed that eddy currents induced in fault zones during magnetic storms could heat the rock by several degrees over the course of hours. This heating would reduce the friction coefficient along fault surfaces, effectively weakening the fault and making it more likely to slip. For a fault already loaded to near failure, this reduction in strength could be the final factor that triggers rupture. There's yet another piece to this puzzle: atmospheric and temperature effects. Research published in 2024 by a Japanese team led by Matheus Henrique Junqueira Saldanha added an interesting dimension to our understanding. They found that solar activity doesn't just affect Earth electromagnetically, it also affects Earth thermally, and these thermal effects might propagate down into the shallow crust. During solar maximum increased solar irradiation, due to flares and enhanced solar activity, creates a tiny but measurable increase in Earth's surface temperature, about 0.1 to 0.2 degrees Celsius. This might seem trivial, but remember that temperature changes affect everything in the Earth system. They affect atmospheric pressure, which loads and unloads the crust. They affect rainfall and snowmelt, which alter water content in the upper crust. They affect rock thermal expansion in the upper few kilometers of the crust. The Japanese team's modeling suggested that these thermal and hydrological effects could alter stress conditions in the upper crust, the zone from the surface down to about 10 kilometers depth, where most earthquakes occur. This is exactly the depth range where electromagnetic effects would also be strongest, because it's closest to the ionosphere where the driving currents flow. What emerges is a picture of multiple mechanisms operating in concert. The electromagnetic effects, piezoelectric strain, and resistive heating act on timescales of hours. The thermal and hydrological effects act on timescales of days to weeks. Together, they could create a cumulative stress perturbation that, while small compared to tectonic forces, might be just enough to trigger faults that are already on the verge of failure. One of the most common mistakes people make when thinking about earthquake triggering is expecting the trigger to be as powerful as the earthquake itself. That's not how triggering works. An earthquake releases energy that has been stored in the crust over decades or centuries through tectonic deformation. The trigger doesn't need to provide that energy, it just needs to overcome the final barrier preventing release. Think of a landslide. It takes years for weathering to weaken the slope for water to infiltrate the soil for the mass to reach an unstable configuration. But the actual trigger might be a single raindrop, a tiny vibration, one extra grain of sand. The trigger isn't providing the gravitational potential energy. It's just overcoming the last bit of resistance. Laboratory experiments have confirmed the principle. Researchers have subjected rock samples to stress levels just below their failure point, then applied small additional stresses, vibrations, pressure pulses, thermal variations. In many cases, these tiny perturbations trigger failure that otherwise would have occurred seconds or minutes later anyway. The trigger advances the timing, but doesn't fundamentally change what was already going to happen. This concept of triggering versus causing is crucial for understanding the sun-earthquake connection. Solar activity isn't creating earthquakes in tectonically stable regions. It's potentially influencing the timing of earthquakes in regions where faults are already critically stressed, already seconds or hours or days away from rupturing anyway. Can you imagine how strange and beautiful this is? We live on a planet where processes happening 93 million miles away in the sun's corona can subtly influence the precise moment when stressed rock finally breaks, when stored tectonic energy suddenly releases, when the ground begins to shake. Not through mystical action at a distance, not through astrological influence, but through a chain of physical processes, electromagnetic, thermal, mechanical, each link in the chain, understandable, measurable, governed by the laws of physics. Yet understanding the mechanism is only part of the story. To truly evaluate whether the sun influences earthquakes, we need to look at the long-term patterns, the historical record stretching back centuries before. We had satellites and seismometers. We need to see if the correlation holds not just over 20 years, but over 400 years, across different solar cycles, through periods of intense activity and profound quiet. Because if this connection is real, It should echo through time, visible in the careful records kept by observers who didn't know what they were documenting, but who wrote down year after year when the ground shook and when the sun raged. There's something almost haunting about reading earthquake records from the year 1650. The handwriting is ornate, careful, the language archaic. A Jesuit priest in Peru describes the ground rolling like ocean waves. A merchant in China notes how temple bells rang without being touched. A Dutch sailor records how the waters of Tokyo Bay suddenly withdrew, then surged back with terrible force. These observers had no seismographs, no moment magnitude scales, no understanding of plate tectonics. But they were meticulous, and they wrote everything down. 410 years of human observation, preserved in archives and monastery records and ship logs across the world. And hidden within these ancient pages is a pattern that spans centuries, a whisper of correlation between the sun's 11-year heartbeat and the Earth's violent shudders. When researchers finally compiled all this scattered data and laid it against records of solar activity reconstructed from sunspot observations, tree rings, and ice cores, what emerged was a story that stretched across the Maunder Minimum, the Dalton Minimum, through Industrial Revolution and World Wars, telling us something profound about the relationship between our planet and its star. If this journey through centuries of observation speaks to your love of deep scientific investigation, please take a moment to like this video and subscribe to Sleepy Science. Your support helps us explore these vast timescales and hidden patterns together. The challenge of studying sun-earthquake correlations over centuries is immediately obvious for most of human history. We had neither seismographs nor satellites. The first crude seismoscope that could reliably detect distant earthquakes wasn't invented until the 1880s. Modern calibrated seismographs didn't exist until the 1930s. Satellites monitoring the solar wind appeared only in the 1960s and 1970s. So, how can we possibly investigate patterns stretching back to 1600? The answer lies in historical seismology and solar physics working together, reconstructing the past from fragmentary evidence. For earthquakes, researchers have compiled historical catalogs by scouring archives, monastery records, government documents, ship logs, newspaper accounts, personal diaries. These sources don't give us precise magnitudes or focal depths, but they do tell us when significant earthquakes occurred, where they occurred, and often something about their intensity based on the damage described. The ISC-GEM Global Instrumental Earthquake Catalog, which we discussed earlier, extends back to 1904, when the first global network of seismographs began operating. But regional catalogs extend much further. Japan has earthquake records stretching back over 1,000 years. China's historical earthquake catalog covers more than 3 millennia. Europe's archives document major earthquakes back to Roman times. By combining these sources, researchers have assembled a reasonably complete record of major earthquakes, those above magnitude 6 or so, for the past 4 to 5 centuries. For solar activity, the primary historical record comes from sunspot observations. Various astronomers have systematically observed and counted sunspots since Galileo first turned his telescope toward the sun in 1610. These observations have gaps, particularly during the Maunder Minimum, when sunspots were so rare that observers sometimes went weeks without seeing any. But the record is continuous enough to reconstruct the solar cycle's behavior over 4 centuries. For periods before systematic observation, scientists use proxy data. Tree rings, for instance, record cosmic ray bombardment, which varies inversely with solar activity. When the sun is quiet, more cosmic rays reach Earth and create isotopes that trees incorporate into their annual growth rings. Ice cores from Greenland and Antarctica contain similar isotopic signatures. These proxies allow us to estimate solar activity levels back thousands of years with reasonable accuracy. In 2011, a research team led by Tavares published a comprehensive study examining earthquake occurrence from 1600 to 2010 in relation to solar cycle phases. This was an ambitious undertaking, 410 years of data spanning 37 complete solar cycles. What they found was striking the relationship between solar activity and earthquake frequency was not constant across all time periods or all regions, but certain patterns emerged consistently. From 1600 to 1645, earthquake frequency in several tectonic regions showed clear increases during solar maxima. This was particularly notable in the Pacific Plate, the Arabian Plate, and the South American subduction zones. During this period, the sun was still relatively active, completing several normal solar cycles. Then came the Maunder minimum. The Maunder minimum from 1645 to 1720 represents one of the most remarkable periods in solar history. For 75 years, sunspots almost completely disappeared. Observers would sometimes see a single small sunspot group in an entire year, or none at all. This wasn't a failure of observation. Multiple astronomers across Europe confirmed the absence of spots. The sun had entered a grand minimum, a state of profound quiet that occurs perhaps once or twice per millennium. What happened to earthquakes during this period? The data shows a significant decrease in the frequency of major seismic events globally. This doesn't mean earthquakes stopped, tectonic forces continued operating as always. But the rate at which major earthquakes occurred declined measurably. When researchers performed statistical analysis comparing earthquake frequency during the Maunder minimum to periods immediately before and after, the difference was significant. This is powerful evidence because the Maunder minimum was a period unlike any other in the observational record. It wasn't just a normal solar minimum, it was an extended absence of solar activity lasting 3/4 of a century. If solar activity influences earthquake triggering, we would expect to see reduced earthquake frequency during such a profound, quiet period. And that's exactly what the historical record shows. The Maunder minimum had other observable effects on Earth. Europe experienced some of the coldest winters in recorded history. During this period, the River Thames in London froze solid, regularly thick enough for frost fairs with booths and bonfires on the ice. Alpine glaciers advanced, destroying mountain villages. Crop failures became common. This period is often called the Little Ice Age. And while solar activity wasn't the only cause, volcanic eruptions also played a role. The coincidence of reduced solar activity and cooler climate is well established. But here's what makes the seismic observations particularly interesting. The cooling climate itself might have affected earthquake frequency through thermal contraction of rock and changes in crustal loading as glaciers advanced. Separating the direct electromagnetic effects of reduced solar activity from the indirect effects of climate change is challenging. This is a perfect example of how Earth system science requires considering multiple interacting processes simultaneously. After the sun emerged from the Maunder minimum, around 1720 solar cycles resumed their normal pattern, and earthquake frequency gradually increased, returning to pre-Maunder levels by the mid-1700s. Then, in the late 1700s, the sun entered another grand minimum, though not as profound as the Maunder, the Dalton minimum, lasting from 1790 to 1820. The Dalton minimum was characterized by several exceptionally weak solar cycles. Sunspots didn't disappear entirely as they had during the Maunder minimum, but their numbers were far below normal. Solar Cycle 5, which peaked around 1804, was the weakest cycle in the modern record until recently. And once again, the earthquake data shows a pattern. During these 30 years of reduced solar activity, the frequency of major earthquakes declined, though not as dramatically as during the Maunder minimum. What's particularly interesting about the Dalton minimum is that we have better earthquake records for this period than for the Maunder minimum. The 1790s through 1820s were a time of extensive European colonization, improved communications, and more systematic record-keeping. The historical earthquake catalog for this period is much more complete and reliable, The observed decrease in seismicity during the Dalton minimum thus carries more statistical weight. The Dalton minimum also coincided with notable climate effects. The year 1816 became known as the year without a summer, following the massive eruption of Mount Tambora in Indonesia in 1815. Snow fell in New England in June. Crops failed across Europe and North America. But the cold period had actually begun earlier in the decade, consistent with the solar minimum's influence on climate. After 1820, as the sun returned to more normal levels of activity, something remarkable happened. Earthquake frequency not only recovered, but began showing an increasingly clear pattern of correlation with the 11-year solar cycle. From 1820 onward, multiple studies have found statistical evidence for enhanced earthquake activity during solar maxima, particularly in seismically active regions. This post-1820 pattern is where we see the clearest evidence for solar earthquake correlation in the historical record. The Tavares study found that earthquake frequency in the Pacific Ring of Fire, the Arabian Plate, and South American subduction zones showed statistically significant peaks during solar maxima. The correlation wasn't perfect. Not every solar maximum coincided with increased seismicity, and not every earthquake cluster occurred during solar active periods. But the overall pattern was there, persistent across multiple solar cycles. Let's look at some specific examples to make this concrete. The solar maximum of 1859 to 1860, the same period that produced the Carrington event, was associated with several major earthquakes. On January 9, 1857, the Fort Tejon earthquake struck Southern California with an estimated magnitude of 7.9, rupturing the San Andreas Fault for nearly 300 kilometers. In 1868, during the declining phase of the same solar cycle, a magnitude 6.8 earthquake devastated San Francisco, killing 30 people. In Ecuador, the 1868 Ibarra earthquake killed an estimated 70,000 people. Now, we must be careful here. I'm not claiming the Carrington event caused these earthquakes. That would be an enormous overreach. What I'm pointing out is that this solar maximum, one of the strongest in recorded history, coincided with a period of notable seismic activity around the Pacific Ring of Fire. Is this correlation or causation? The historical record alone can't tell us definitively. Another interesting period is the early 1900s. Solar cycle 14, which peaked around 1906, was a particularly strong cycle. And 1906 saw one of the most famous earthquakes in American history. The San Francisco earthquake of April 18th, magnitude 7.9, which destroyed much of the city and killed over 3,000 people. In the same year, a magnitude 8.8 earthquake struck off the coast of Ecuador and Colombia, triggering a tsunami that killed between 500 and 1,500 people. In 1905, just months before these events, the Kangra earthquake in India killed an estimated 20,000 people. Again, correlation isn't causation. These earthquakes occurred because the Pacific Plate and its boundaries were and are under immense tectonic stress. The San Andreas Fault had been accumulating strain for decades. The San Francisco earthquake was inevitable. But the timing, the fact that it occurred during an active solar period, fits the pattern we've been discussing. One of the most important lessons from examining 4 centuries of data is understanding what we should and shouldn't expect to see. A common mistake is expecting that if solar activity influences earthquakes, every solar maximum should produce major earthquakes everywhere, and every solar minimum should be seismically quiet. That's not how triggering works, and it's not what the data shows. Remember, earthquakes are primarily driven by tectonics. The slow grinding of plates builds up stress over years and decades. Whether solar activity can trigger an earthquake depends entirely on whether a fault is already near failure. In regions where no faults are critically stressed, solar activity should have no effect. In regions where faults are near failure, solar activity might advance the timing of earthquakes that were going to happen anyway. This means we should expect the solar earthquake correlation to be strongest in the most seismically active regions. places where faults are constantly approaching failure, and that's exactly what the data shows. The Pacific Ring of Fire, the Arabian Plate boundary, the South American subduction zones. These are the regions where the historical data shows the clearest correlations between solar activity and earthquake frequency. There's also the question of earthquake size. The historical record suggests that the correlation is stronger for larger earthquakes. This makes physical sense. Larger earthquakes involve larger fault surfaces and larger volumes of stressed rock. They might be more susceptible to external triggering because the stress is distributed over a larger area, increasing the probability that somewhere along that fault surface, the stress is close enough to failure that a small trigger could matter. The Tavares study, and others like it, reveal something else important. The correlation between solar activity and earthquakes appears to have strengthened over time. The pattern is clearer in the 19th and 20th centuries than it was in the 17th and 18th centuries. Why might this be? One possibility is simply better data. Earlier records are incomplete, biased toward populated regions, and less reliable in terms of timing and location. Modern records are comprehensive and precise. A pattern that was always there might simply be easier to detect with better data. But there's another intriguing possibility. Earth's magnetic field has been changing. Over the past 4 centuries, Earth's magnetic field has weakened by about 10 to 15%. This weakening affects how efficiently solar wind energy couples into the magnetosphere and ultimately into the ground. Some researchers speculate that as the field weakens, electromagnetic coupling might become more efficient, making any solar earthquake connection stronger. This remains speculative, but it's an interesting hypothesis that could be tested as the magnetic field continues to evolve. Have you ever wondered if the patterns we see in nature are telling us something fundamental about how different parts of our planetary system interact? Or if our pattern-seeking minds sometimes find order where only chaos exists? This question haunts every researcher who works with historical data. And it's why modern scientists demand such rigorous statistical testing. The historical record spanning grand solar minima and maxima quiet periods and active periods gives us something the 20-year SOHO dataset cannot. Perspective across timescales longer than a single solar cycle. It shows us that whatever connection exists between sun and earthquakes is subtle, statistical, and embedded in the complex system of tectonic forces that primarily drive seismicity. But it also shows us that the pattern is persistent, appearing again and again across centuries. Yet for all this historical evidence, for all the patterns that emerge when we analyze centuries of records, we still face profound skepticism from the scientific community. Because finding patterns in data, even across 4 centuries, isn't enough to convince scientists who know how easily humans can be deceived by randomness, who understand how many ways statistical analysis can go wrong, who have seen countless claimed correlations evaporate under rigorous scrutiny. The controversy surrounding solar earthquake connections is fierce, thoughtful, and absolutely essential to the scientific process. In 2013, a team of American researchers published a paper with a title that was diplomatic but devastating. They had analyzed the same question: does solar activity trigger earthquakes? And their conclusion was unequivocal: no. No statistically significant correlation. No evidence for triggering, nothing. They examined different time periods, different magnitude thresholds, different statistical methods, and in every case they found that earthquake occurrence was indistinguishable from what you'd expect from random chance. Their paper directly contradicted decades of previous research, including studies we've discussed, that claim strong correlations. And here's what makes this moment so important for understanding how science actually works. Both sides might be partly right. The Italian team's 2020 finding of a 1 in 100 Saharan probability of random correlation, and the American team's 2013 conclusion of no significant correlation aren't necessarily contradictory. They might be looking at different aspects of an enormously complex phenomenon, asking slightly different questions, using different statistical assumptions, and arriving at legitimately different conclusions that reveal just how difficult it is to extract clear signals from noisy data in a chaotic system. If you're intrigued by how science wrestles with uncertainty and contradiction, I'd be grateful if you'd like this video and subscribe to Sleepy Science. These moments of scientific debate are where real understanding emerges, and I'm honored to explore them with you. The 2013 study was conducted by Jeffrey Love and Jeremy Thomas at the United States Geological Survey, one of the world's premier institutions for earthquake research. Their approach was methodical and comprehensive. They took the same basic hypothesis that solar activity influences earthquake occurrence and tested it using multiple statistical methods, multiple earthquake catalogs, multiple measures of solar activity, and multiple time periods. This is exactly what you want to see in science-independent researchers with access to similar data, applying rigorous methods to test whether a claimed phenomenon is real. Love and Thomas examined the relationship between earthquake frequency and various measures of solar activity, including sunspot number, solar radio, flux, geomagnetic indices, and cosmic ray intensity. They looked at global earthquake occurrence and regional patterns. They examined different magnitude thresholds from magnitude 5 to magnitude 7 and above. They considered various time lags between solar activity and earthquake occurrence. They applied standard statistical tests to see if the distribution of earthquakes differed significantly between periods of high and low solar activity. Their conclusion was stark. They found no statistically significant correlation. The distribution of earthquakes during high solar activity periods was not meaningfully different from the distribution during low solar activity periods. When they accounted for the natural clustering of earthquakes, the fact that aftershocks follow main shocks, the apparent patterns disappeared. They could not reject what statisticians call the null hypothesis, the hypothesis that solar activity has no effect on earthquake occurrence. This is a direct challenge to the Italian 2020 study and to decades of earlier research. How can we reconcile these contradictory findings? The answer reveals something crucial about the nature of scientific investigation and the challenges of studying complex systems. First, there's the question of what exactly you're measuring. The Italian team focused specifically on proton density in the solar wind, as measured by SOHO, while Love and Thomas looked at broader measures of solar activity, including sunspot number and geomagnetic indices. These aren't the same thing. Sunspot number is a proxy for overall solar magnetic activity, but it doesn't directly measure the particle flux reaching Earth. Geomagnetic indices measure Earth's magnetic field response to solar wind, but they integrate effects over hours or days and might miss transient spikes in proton density. If the mechanism by which solar activity triggers earthquakes involves specific bursts of high-density protons, as the Italian team's hypothesis suggests, then looking at smooth averages of solar activity might miss the signal entirely. It's like trying to detect lightning strikes by measuring average atmospheric electrical potential over 24-hour periods. You'd miss the crucial brief spikes that actually matter. Second, there's the magnitude threshold question. The Italian team found that the correlation strengthened dramatically when they looked at larger earthquakes magnitude 6.0 and above, particularly 6.5 and above. Love and Thomas included many smaller earthquakes in their analysis, including events down to magnitude 5.0. If solar triggering is most effective for large, already stressed fault systems, diluting the data set with smaller earthquakes might obscure the signal. Third, there's the statistical methodology. Love and Thomas used what's called a distribution comparison approach. They looked at whether the overall distribution of earthquake numbers differed between high and low solar activity periods. The Italian team used an event-based approach. They looked at whether individual high proton density events were followed by increased earthquake rates in the subsequent 24 hours. These are different questions with different statistical power to detect different types of correlations. Imagine you're trying to determine whether full moons affect human behavior. You could compare crime rates during full moon weeks versus new moon weeks, or you could look at whether individual nights with full moons show spikes in emergency room visits. These are related questions, but they might give different answers depending on the nature and magnitude of any real effect. In 2022, another comprehensive study was published by Iranian researchers Mehdi Akhundzadeh and colleagues, and their findings added yet another layer to the controversy. They examined 333 large earthquakes magnitude 7.0, and above that occurred between 2000 and 2022. They looked at multiple solar and geomagnetic indices, including the F10.7 solar flux, the KP and API geomagnetic indices, and the DST disturbance storm time index. Their goal was to see if anomalies in these indices appeared before earthquakes. They found that approximately 33% of the earthquakes in their sample were preceded by anomalous variations in solar and geomagnetic indices one day before the event. That sounds significant, 1/3 of major earthquakes showing precursor signals. But here's where their analysis becomes devastating to the solar earthquake hypothesis. They also analyzed 100 simulated random data sets, where earthquake times were randomly shuffled. And they found that these random data sets showed similar percentages of apparent precursor anomalies. In other words, if you just randomly pick dates and look for solar or geomagnetic anomalies within a day or two of those dates, you'll find anomalies about 1/3 of the time anyway, simply because solar and geomagnetic activity varies frequently. The apparent precursor signal was indistinguishable from what you'd expect by chance. Their conclusion was unambiguous. There is no significant correlation between solar and geomagnetic indices and the occurrence of strong earthquakes. This is a crucial lesson in the pitfalls of pattern recognition. Our brains are extraordinarily good at finding patterns, but they're not good at assessing whether those patterns are meaningful or just random noise. When you look at a time series of solar activity, which varies constantly, and a time series of earthquakes, which also vary constantly, you will always find instances where they seem to align. The question is whether these alignments occur more often than pure chance would predict. And answering that question rigorously requires sophisticated statistical analysis and careful consideration of multiple comparisons, selection biases, and natural variabilities in both data sets. The Iranian team's methodology of testing against randomly shuffled data is called a Monte Carlo simulation, and it's one of the most powerful tools for detecting false patterns. If your claim signal disappears when you shuffle the data randomly, then your signal probably wasn't real. To begin with, it was just an artifact of how you selected or analyzed the data. So, why did the Italian team find such a strong correlation if it might not be real? There are several possibilities, and understanding them is essential for appreciating how difficult this research actually is. One possibility is that the Italian team's finding is real, but specific to the particular way they defined and measured the correlation. Perhaps the connection between proton density spikes and earthquakes is real, but narrow, requiring specific thresholds, specific time lags, specific magnitude ranges, and other studies missed it by using slightly different parameters. This would mean the phenomenon is real, but fragile, easily obscured by variations in methodology. Another possibility is publication bias and the file drawer problem. Here's how this works. Imagine 100 research teams independently analyze the solar earthquake question. By chance alone, about 5 of them will find statistically significant correlations at the standard 5% significance level, even if no real effect exists. Those 5 teams publish their findings because significant results are publishable. The other 95 teams find nothing and don't publish because negative results are harder to publish. The literature then becomes biased toward false positives, apparent effects that are actually just statistical flukes. This is a pervasive problem in science, particularly in fields where data is noisy and effects are small. It's not that researchers are being dishonest, they're following standard practices. But the cumulative effect is that published research gives a misleading impression of the evidence. There's also the challenge of defining what counts as a correlation. The Italian team found that earthquakes were more likely in the 24 hours following high proton density events. But more likely is a relative term. If the baseline rate is 1 earthquake per day globally above magnitude 5.6, and high proton density days show 1.2 earthquakes per day, that's a 20% increase statistically detectable with enough data. But is it physically meaningful? Is it large enough to call it triggering? Moreover, earthquakes themselves are not Poisson distributed. They don't occur randomly in time. They cluster due to aftershock sequences which can last for months or years after major events. They show spatial clustering along active plate boundaries. They might show seasonal variations due to hydrological loading and other factors. Any correlation with solar activity has to be detected against this background of natural variability and clustering, which makes the statistical analysis extraordinarily complex. Here's another complication that's often overlooked: the problem of what statisticians call multiple testing, or p-hacking. When you have a data set, you can analyze it in many different ways. You can look at different magnitude thresholds, different time lags, different geographic regions, different measures of solar activity, different statistical tests. If you try enough combinations, you'll eventually find one that gives a statistically significant result, purely by chance. This is why pre-registration of analysis plans deciding in advance exactly what you'll test, and how is becoming standard practice in many fields. Did the Italian team try many different approaches and report the one that worked? Their paper doesn't suggest this. They seem to have had a clear hypothesis and tested it directly. But the question remains whether other researchers tried similar approaches and found nothing, leaving those negative results unpublished. In 2021, Russian physicist Gennady Sobolev, one of the pioneers of solar earthquake research, published a study that took a different approach. Instead of looking at continuous correlations, he examined the timing of specific major earthquakes relative to specific major magnetic storms. Between 1994 and 2017, he identified 50 of the strongest magnetic storms, those with planetary KP index above 7, and looked at whether major earthquakes, magnitude 6.5 and above, were more likely to occur in the 2 days following these storms. He found that 17 major earthquakes occurred within 2 days of the 50 strongest storms. Statistical analysis suggested this was more than would be expected. By chance, the probability was above 95% that this wasn't random. But note the difference from the Italian study. Sobolev's finding was less statistically strong, 95% versus 99.9999%, looked at a smaller sample and focused specifically on the very strongest magnetic storms and largest earthquakes. This brings us to an important realization. Perhaps the truth is somewhere in the middle. Perhaps there is a weak, subtle conditional effect, where the very strongest solar wind disturbances can trigger the very largest earthquakes that are already on the verge of rupture. But this effect is so small and so conditional that it's difficult to detect consistently with different methodologies. It would be real, but barely detectable, strong enough to occasionally show up in statistical analyses, but weak enough to be overwhelmed by noise and natural variability in most analyses. One of the most common misconceptions in this debate is the assumption that if solar activity doesn't consistently correlate with all earthquakes everywhere, then it correlates with none. This is black and white thinking that misses the possibility of a nuanced reality. Nature rarely works in absolutes. Effects can be real, but conditional, present under some circumstances, but not others, strong enough to matter sometimes, but not always. There's also a geographical consideration that's crucial. Jeffrey Love and Jeremy Thomas, the USGS researchers who found no correlation, were primarily looking at California seismicity, a specific region with specific tectonic characteristics. The Italian team looked at global seismicity. Different tectonic settings might respond differently to solar forcing, depending on local stress states, crustal conductivity, fault geometry, and many other factors. Perhaps the most important lesson from this controversy is about the nature of scientific uncertainty. In popular science communication, we often present science as having clear answers. This theory is right, that theory is wrong. But real science at the frontier of knowledge is messy, uncertain, and full of disagreement. And that's not a weakness, it's a strength. The disagreement drives researchers to collect better data, develop better statistical methods, think more carefully about mechanisms, and gradually converge on truth. The debate over solar earthquake connections is far from settled, and in a sense that's exactly how it should be. We have intriguing correlations from some studies, null results from others, plausible mechanisms that might work, and enormous challenges in detecting small effects in noisy data. What we don't have is consensus, and we shouldn't pretend otherwise. Think about this: if you were designing a system to trigger earthquakes from space using the solar wind as your mechanism, would you design it to be barely detectable to work, only sometimes to affect only certain regions, to be strong enough to show up in 20 years of satellite data, but weak enough to disappear when you analyze it differently? Probably not. You design something clear and unambiguous. The fact that the solar earthquake connection, if it exists at all, is so subtle and difficult to confirm, might tell us something profound about the magnitude of the effect, real perhaps, but tiny compared to the massive tectonic forces that primarily drive earthquakes. But here's where the story takes a practical turn, because even if the correlation is weak and controversial and disputed, the question remains: could monitoring solar activity give us any useful information for earthquake forecasting? Could it be one piece of a larger puzzle, one factor among many that together might help us anticipate when and where the ground might shake? The implications for prediction and preparedness are what drive much of the research, and they're what make this controversy matter beyond academic debate. Imagine waking up to an alert on your phone that reads, "High solar wind activity detected. Increased seismic probability for the next 24 hours in your region. Review your emergency preparedness." This isn't science fiction, it's a plausible near-future application if the solar earthquake connection proves robust. But here's the profound dilemma that keeps seismologists awake at night. Earthquake prediction is perhaps the most challenging problem in all of Earth science, a problem where decades of research have yielded more failures than successes, where false alarms can cause panic and economic disruption, where missed predictions can mean catastrophic loss of life. Adding solar activity monitoring to the prediction toolkit sounds promising, but it raises questions as troubling as they are important. If solar wind spikes increase earthquake probability by 20% in regions where faults are already stressed, do we warn people? And if we do warn them, what exactly should they do? Evacuate. That's economically impossible for regions of millions of people. Stay alert. That might save some lives, but it also might create a society living in constant anxiety, responding to alerts that 99 times out of 100 lead to nothing. If you're finding this exploration of the practical implications of space-Earth connections as thought-provoking as I do, please consider liking this video and subscribing to Sleepy Science. These questions about how we apply scientific knowledge matter deeply, and I'm grateful we can explore them together. Let's begin with the stark reality of earthquake prediction as it exists today. Despite billions of dollars invested in research, despite global networks of sensors, despite sophisticated models of tectonic stress, we cannot predict earthquakes in any operationally useful way. We can identify regions where earthquakes are likely over decades, plate boundaries, active fault zones of historical seismicity. We can calculate probabilities. There's a 72% chance of a magnitude 6.7 or larger earthquake striking the San Francisco Bay Area before 2043. But we cannot say when the next earthquake will strike with anything resembling the precision and accuracy that would allow people to take meaningful protective action. Why is earthquake prediction so difficult? The fundamental problem is that earthquakes are the result of a complex system with multiple interacting variables, sensitive dependence on initial conditions, and what physicists call critical point behavior. Think of a pile of sand. You can keep adding grains, watching it grow taller, but you cannot predict which specific grain will trigger an avalanche. The system is deterministic. It follows physical laws, but it's also chaotic, meaning tiny, unmeasurable differences in initial conditions lead to completely different outcomes. Earthquakes work similarly. Stress builds up along a fault as tectonic plates grind against each other. But the fault isn't uniform. It has rough patches and smooth patches, strong sections and weak sections, areas where fluids circulate and areas that are dry. The stress distribution is heterogeneous and constantly evolving as small slip events redistribute stress, as seasonal rainfall changes pore pressure, as thermal expansion and contraction affect rock properties. All these factors interact in complex, nonlinear ways. The result is that a fault can sit in a critically stressed state for months or years, ready to rupture but not quite rupturing, and nothing we can currently measure tells us whether it will slip today, tomorrow, or 10 years from now. We're trying to predict the behavior of a system with billions of variables, most of which we can't measure, governed by equations we can't fully solve. This is the context into which the solar earthquake hypothesis enters. If confirmed solar activity monitoring wouldn't solve the prediction problem, it would merely add one more variable to the complex equation. But it might be a useful variable, one that changes on timescales of hours to days, and could potentially shift probabilities in measurable ways. How would this actually work in practice? Let's think through a concrete scenario. Imagine it's 2030 and the scientific community has reached consensus that strong solar wind events increase earthquake probability by 30% in tectonically active regions for 24 hours following the event. A space weather satellite detects a massive coronal mass ejection heading toward Earth. Models predict it will arrive in 36 hours with high proton density and magnetic field strength. What happens next? First, space weather forecasters at NOAA's Space Weather Prediction Center issue alerts. These alerts already exist for satellite operators, power grid managers, and airlines, warning them of potential disruptions to GPS communications and radiation exposure at high altitudes. But now there's an additional component: seismic risk assessment. Regional seismological agencies in earthquake-prone areas receive the alert. In California, Japan, Chile, New Zealand, Indonesia regions where major faults are under high stress, seismologists run probabilistic models that incorporate the solar wind forecast, along with current assessments of fault stress, recent seismic activity, geodetic data from GPS networks, and other factors. The models calculate how much the solar wind event might increase the probability of a major earthquake in the next 24 to 48 hours. Here's where it gets complicated. Let's say the baseline probability of a magnitude 6.5 or larger earthquake in the San Francisco Bay Area on any given day is about 0.1%, roughly one chance in 1,000. The solar wind event increases this to 0.13%, a 30% relative increase, but still only 13 chances in 10,000. Should San Francisco's emergency management issue a public alert? The decision involves weighing risks and benefits in ways that are as much social and political as scientific. Issue the alert and you might save lives. If an earthquake does occur, people might review their emergency supplies, avoid being in vulnerable structures, ensure they know how to shut off gas lines. But you also might cause economic disruption as people stay home from work, cancel travel plans, or panic unnecessarily. And if you issue alerts frequently but earthquakes rarely follow, people will stop paying attention, the cry wolf effect. that undermines all future warnings. Don't issue the alert and you avoid the disruption, but potentially miss an opportunity to enhance preparedness. If the earthquake does occur, there will be intense criticism. The scientists knew the risk was elevated. Why didn't they warn us? This is not a hypothetical dilemma. It's exactly the situation seismologists faced in L'Aquila, Italy in 2009. In the months before a devastating magnitude 6.3 earthquake that killed 309 people, the region experienced hundreds of small tremors and earthquake swarm. A commission of scientists was convened to assess the risk. They concluded that while the swarms were concerning, they did not necessarily indicate an imminent major earthquake. Many earthquake swarms are not followed by large events. Their assessment was communicated to the public in a way that was interpreted as reassurance that there was no danger. When the earthquake struck on April 6, 2009, killing over 300 people, 6 scientists and 1 government official were charged with manslaughter for allegedly providing falsely reassuring statements that caused people to let down their guard. They were initially convicted of a verdict that shocked the international scientific community, though most convictions were later overturned on appeal. The message was chilling. Scientists could face criminal liability for their risk assessments, whether they warned or didn't warn, whether the predicted event occurred or didn't occur. This is the minefield into which solar-based earthquake forecasting would enter. The potential benefit is real. If we could identify periods of elevated risk, even small elevations, we might save lives through enhanced preparedness. But the potential for misuse, misinterpretation, false alarms, and unintended consequences is equally real. One approach that might navigate these challenges is probabilistic forecasting rather than deterministic prediction. Instead of saying an earthquake will occur, you say the probability of an earthquake in the next 24 hours is X%, which is Y% higher than the baseline. This honestly communicates both the risk and the uncertainty. It empowers people to make their own decisions about whether to take extra precautions without creating panic or false certainty. New Zealand has pioneered this approach with their Earthquake Forecasting and Testing Center. After major earthquakes, they issue probabilities for aftershocks of various magnitudes over specific time periods. There's a 25% chance of a magnitude 6 or larger aftershock in the next week, is a very different message from a magnitude 6 aftershock will occur. And it's a message people can use to make informed decisions about returning to damaged buildings or staying in affected areas. Solar activity monitoring could fit naturally into this framework. Today's solar wind conditions increase seismic probability by 20% above baseline, provides actionable information without overstating our predictive capabilities. People in earthquake-prone regions could choose to check their emergency kits, remind themselves of earthquake safety procedures, or simply maintain heightened awareness, all without requiring disruptive evacuations or causing panic. But even this probabilistic approach has challenges. Most people are not skilled at interpreting probabilities, especially small probabilities. A 30% increase in a probability that was already very small might sound alarming, but still represents an extremely low absolute risk. Communicating this clearly without causing confusion or complacency is a significant challenge in risk communication. There's also the question of geographic specificity. The Italian study found global correlations but with regional variations. Some tectonic boundaries seemed more responsive to solar forcing than others. If solar earthquake forecasting is to be useful, we need to understand which specific faults or fault systems are most susceptible, which geological conditions enhance the effect, which orientations and stress states make. Faults responsive to electromagnetic triggering. This requires detailed regional studies combining seismology, geology, electromagnetic surveying, and space physics. Truly interdisciplinary research that spans traditional boundaries between fields. It requires long-term monitoring to build up statistical power for detecting effects at the regional scale. and it requires careful validation to ensure that apparent regional differences aren't just artifacts of data quality recording, completeness, or analytical methods. Let's consider a specific example of how this might work. Japan has the densest seismological monitoring network in the world, sophisticated earthquake early warning systems, and a population that is well educated about seismic risk and preparedness. Japan also maintains advanced space weather monitoring capabilities through collaborations with international space agencies. If any country could implement solar-based earthquake risk forecasting, it would be Japan. Imagine a Japanese system that integrates real-time solar wind data from satellites with regional stress models derived from GPS networks, monitoring crustal deformation, seismological networks, tracking background seismicity, and geological databases, characterizing fault properties and conductivity structure. Machine learning algorithms trained on decades of historical data could identify patterns that optimize prediction skill, which combinations of solar wind parameters, fault characteristics, and current stress levels most reliably precede increased seismic activity. When conditions align, high proton density, critically stressed fault, high crustal conductivity, the system issues graduated alerts. A level 1 alert might go to seismologists and emergency managers, only prompting them to review monitoring data more frequently. A level 2 alert might be sent to critical infrastructure operators, nuclear plants, dams, major bridges, prompting checks of safety systems. A level 3 alert might be communicated to the general public through the National Emergency Alert System, suggesting enhanced preparedness without recommending evacuation. This graduated approach allows responses proportional to the assessed risk, while providing valuable information at multiple levels. It also generates data for ongoing validation. Every alert, whether followed by an earthquake or not, provides information about the performance of the forecasting system, allowing continuous improvement through machine learning and statistical refinement. The Project CSES Limado satellite mission, launched by China and Italy in 2018, represents exactly this kind of forward-looking approach. The satellite is specifically designed to study possible connections between space weather, ionospheric disturbances, and seismic activity. It carries instruments to measure electromagnetic fields, charged particle fluxes, and plasma parameters, all while monitoring seismic activity on the ground below. The mission's goal is to test whether electromagnetic anomalies in space can serve as earthquake precursors, and to understand the physical mechanisms that might connect them. Early results from CSS have detected electromagnetic anomalies before some major earthquakes, though the challenge remains distinguishing real precursors from false alarms and natural variability. This is the kind of research sustained, systematic with purpose-built instruments that will ultimately determine whether solar and electromagnetic monitoring can contribute meaningfully to earthquake forecasting. But we must be honest about the limitations. Even in the most optimistic scenario, where solar earthquake connections prove robust and regionally predictable, we're talking about forecasting windows of 24 to 48 hours with modest probability increases. This is not the kind of prediction that allows for evacuations or major disruptions to daily life. It's more akin to weather forecasts that warn of increased tornado probability. You don't evacuate cities, but you do pay attention to the sky and know where your shelter is. Moreover, solar triggering, if real, is just one of many external factors that might influence earthquake timing. Tides exert measurable stress on faults. The gravitational pull of the moon and sun that raises ocean tides also raises earth tides that periodically load and unload faults. Some studies have found weak correlations between tidal phase and earthquake occurrence, though other studies have found no effect. Seasonal rainfall and snowmelt change water loading on the crust and pore pressure in fault zones. Atmospheric pressure variations load the crust differently in winter versus summer. Even the filling of large reservoirs behind dams has been linked to triggered seismicity in some cases. A comprehensive earthquake forecasting system would need to integrate all these factors: tectonic stress from plate motion, tidal stress, hydrological loading, atmospheric pressure, and potentially solar electromagnetic effects into a unified, probabilistic model. Solar monitoring would be one input among many valuable, but not sufficient on its own. The ethical dimensions of earthquake forecasting cannot be overlooked. When you issue an alert that might influence millions of people's decisions, you bear some responsibility for the consequences of both true positives and false positives, both missed events and predicted events that don't occur. This responsibility weighs heavily on scientists and emergency managers who know that lives hang in the balance, but also know that certainty is impossible. There's wisdom and humility here. The most honest thing science can say about earthquake prediction is that we don't know when the next earthquake will strike, but we can identify factors that might modestly increase or decrease short-term risk. Solar activity monitoring might be one such factor. It won't revolutionize earthquake prediction, but it might incrementally improve our ability to assess risk in the days surrounding major space weather events. Think about your own relationship with uncertainty and risk. How much would a 30% increase in earthquake probability change your behavior? Would you find that information useful, or would it simply create anxiety without enabling meaningful action? These are deeply personal questions with no universal answers. What becomes clear through all of this is that the practical implications of the solar earthquake hypothesis extend far beyond the scientific question of whether the correlation is real. They touch on risk communication, public policy infrastructure, resilience, and the role of science in society. They force us to grapple with how we make decisions under uncertainty, how we balance precaution against disruption, how we communicate probability to populations that might not have the background to interpret it correctly. But these practical challenges, daunting as they are, don't diminish the profound beauty of the underlying question: whether or not solar monitoring proves useful for earthquake forecasting. The investigation itself has revealed connections between Earth and space that earlier generations never imagined, has forced us to think about our planet as part of an interconnected solar system, rather than an isolated sphere, has shown us that the ground beneath our feet responds to rhythms written in the stars. We've traveled together through 170 years of scientific investigation, from Rudolf Wolf's curious observation in 1853 to cutting-edge satellite missions orbiting between Earth and Sun. We've examined statistical correlations spanning 20 years of space data, historical patterns reaching back 4 centuries through grand solar minima and maxima, physical mechanisms, connecting electromagnetic energy to mechanical stress in rock, and fierce scientific debates about whether any of this is real. Now, as we arrive at the end of this journey, it's time to step back and ask the deeper question: what does all of this tell us about our place in the cosmos? Whether the sun truly triggers earthquakes, or whether the correlations dissolve under sufficient scrutiny. The investigation itself has transformed how we understand our planet, not as an isolated sphere floating in empty space, but as an active participant in a dynamic solar system, continuously responding to invisible forces that wash over us from 93 million miles away. If this exploration has deepened your appreciation for the hidden connections that bind our world, I'd be honored if you'd like this video and subscribe to Sleepy Science. Your presence on this journey means everything, and I'm grateful for each moment we've spent together exploring these mysteries. Let's begin by taking stock of what we know with confidence. We know without question that solar activity profoundly affects Earth's space environment. The solar wind, coronal mass. Ejections and variations in solar electromagnetic radiation shape our magnetosphere, drive currents in our ionosphere, and induce electrical currents in our crust. These are not theoretical possibilities. They're measured facts observed continuously by satellites and ground stations around the world. Every major geomagnetic storm demonstrates the sun's reach, disrupting satellite operations, creating auroras at unusual latitudes, affecting power grids, and altering the electromagnetic environment from space down to ground level. We know that Earth's crust is not electromagnetically inert. It contains vast quantities of quartz and other materials that respond to electrical fields through piezoelectric effects. It conducts electrical currents through fault zones and fluid-filled rock. Laboratory experiments confirm that electrical currents can heat rock, that heating affects mechanical strength, that stress pulses can trigger failure in critically loaded materials. The physical mechanisms by which electromagnetic energy could influence seismicity are plausible, grounded in established physics, and consistent with what we know about rock mechanics and Earth structure. We know that earthquakes are not purely Poissonian random events. They cluster in space and time, influenced by tectonic stress, aftershock sequences, and potentially by external factors, including tidal forces and seasonal loading. The idea that earthquake timing might be influenced by external triggers is not radical. It's actually expected for faults that are close to failure, where small additional stresses can advance rupture timing. What remains uncertain, and this is crucial, is whether solar activity actually does influence earthquake occurrence in a statistically and practically significant way. The Italian 2020 study presents compelling evidence for correlation. The American 2013 study finds no such correlation. The Iranian 2022 study suggests apparent correlations might be artifacts. 4 centuries of historical data show patterns during grand solar minima that seem too consistent to dismiss as coincidence. But historical data is incomplete, potentially biased, and challenging to analyze rigorously. The honest answer to the question, can the sun trigger earthquakes, is possibly, but the effect, if it exists, is subtle, conditional, and difficult to detect consistently. It's not the dominant factor in seismicity tectonic forces are. It's not a reliable prediction tool. Too many other variables matter more. But it might be real, operating at the margins, influencing timing for faults already on the verge of failure, visible in some data sets and analytical approaches, but not in others. And you know what? That kind of answer, uncertain, nuanced, provisional, is actually how most of science works. We want simple, definitive answers. We want to know whether something is true or false. But nature often gives us complicated, context-dependent phenomena that reveal themselves, gradually requiring decades of careful research, competing hypotheses, and evolution of understanding. The beauty of this investigation lies not just in the answer, but in what the question has forced us to consider. It has revealed that Earth exists within a space environment that's far more dynamic and influential than we once believed. Every moment of every day, we're bathed in particles from the sun, buffeted by the solar wind, connected to our star through invisible threads of magnetic field and electromagnetic energy. The ground we stand on is not isolated from this cosmic environment. It responds to it subtly, perhaps, but responds nonetheless. This realization connects to a broader shift in how we understand Earth. For most of human history, we thought of our planet as the center of everything, with the heavens revolving around us. Copernicus and Galileo displaced us from that center, showing we orbit the sun along with other planets. But we still tended to think of Earth as self-contained, governed by internal forces, plate tectonics, volcanic activity, erosion, weather, with space as a distant, irrelevant backdrop. The past century of research has demolished that isolation. We now know that asteroid impacts have repeatedly reshaped life on Earth, that the moon's formation from a giant collision fundamentally determined our planet's geology and rotation, that solar cycles affect climate in measurable ways, that cosmic rays from distant supernovae may have influenced evolution through their effects on mutation rates, that our entire solar system orbits through the galaxy, passing periodically through spiral arms, where we're exposed to higher levels of radiation. Earth is not an island. It's a node in a vast interconnected system, influenced by processes occurring at every scale, from the quantum mechanics of crystal lattices to the dynamics of our galaxy. The possible Sun-earthquake connection is just one thread in this cosmic tapestry, but it's a thread that connects the microscopic piezoelectric effects in individual quartz crystals to the planetary tectonic forces spanning continents to the interplanetary, the solar wind filling the space between worlds. Let's talk about other ways the sun influences Earth, because understanding this broader context helps us appreciate why the earthquake connection isn't really so strange. The most obvious influence is light and heat. The sun provides essentially all the energy driving Earth's climate and biosphere. But beyond that, there are more subtle connections that have only recently been understood. Solar ultraviolet radiation controls the chemistry of the upper atmosphere, creating the ozone layer that protects life from harmful UV rays. Variations in UV output over the solar cycle affect ozone concentrations, which in turn affect atmospheric circulation patterns. Some climate scientists believe solar cycle variations influence the North Atlantic Oscillation and other large-scale weather patterns through these upper atmospheric effects. Solar energetic particles, particularly during major solar storms, affect atmospheric chemistry in the polar regions, creating nitrogen oxides that deplete ozone. The Carrington event of 1859 likely caused temporary ozone depletion, though we have no direct measurements from that time. Modern satellite data shows measurable ozone depletion following major solar particle events. The solar wind, by modulating the flux of galactic cosmic rays reaching Earth, affects cloud formation. Cosmic rays ionize the atmosphere, and ionization might influence cloud nucleation, the process by which water vapor condenses into droplets. Henrik Svensmark and others have proposed that solar cycle variations affect cloud cover through this mechanism, providing another pathway for solar influence on climate. This remains controversial, with some studies supporting the idea and others finding no effect, but it exemplifies how the sun's influence extends beyond simple radiation. Solar activity affects satellite operations not through earthquakes, but through direct interaction with spacecraft. During major geomagnetic storms, satellites in low Earth orbit experience increased atmospheric drag because the upper atmosphere heats and expands. This orbital decay requires periodic reboost maneuvers, consuming fuel and limiting satellite lifetimes. In 2022, a moderate geomagnetic storm caused the loss of 40 Starlink satellites that had just been launched. The atmospheric expansion was so significant that the satellites couldn't reach stable orbits and re-entered the atmosphere. Power grids are vulnerable to geomagnetically induced currents during major storms. The Quebec blackout of 1989 was just one example. In 1972, a solar storm caused the detonation of Navy sea mines off the coast of Vietnam. Induced currents triggered the magnetic detonators. During the same storm, AT&T's long-distance telephone network experienced disruptions from current surges and buried cables. These are not subtle controversial effects. These are direct, measurable, sometimes catastrophic impacts of solar activity on human technology and infrastructure. They prove beyond doubt that the sun's influence reaches Earth's surface and below through electromagnetic pathways. Given this established fact, the question of whether these same pathways might affect geological processes seems less outlandish and more like a natural extension of what we already know. Looking forward, research in this field will continue with ever-improving tools. The Chinese-Italian CSES Limidu satellite will be joined by additional missions specifically designed to study space-Earth connections. Ground-based monitoring networks are becoming denser and more sophisticated. Machine learning algorithms will be applied to decades of accumulated data, searching for subtle patterns that traditional statistical methods might miss. But perhaps more importantly, the theoretical understanding of the proposed mechanisms will deepen. Researchers are developing more sophisticated models of how electromagnetic energy couples from the magnetosphere-ionosphere system into the crust. They're conducting laboratory experiments on rock mechanics under combined electrical thermal and mechanical stress. They're using supercomputers to simulate the complete chain of events from solar wind impact to fault rupture testing, whether the proposed mechanisms can actually produce observable effects. The Chinese space program has announced plans for an expanded constellation of satellites monitoring electromagnetic fields and particle fluxes specifically for earthquake research. Japan continues to deploy seafloor sensors and GPS networks that provide unprecedented resolution of crustal deformation. The European Space Agency is planning missions to improve solar wind monitoring. These investments suggest that major scientific institutions believe the question is worth pursuing, that the potential payoff justifies the effort. Whether these investigations ultimately confirm or refute the solar earthquake hypothesis, they will advance our understanding. If confirmed, we gain insight into earthquake-triggering mechanisms and potentially a new tool for hazard assessment. If refuted after thorough investigation, we gain confidence that seismicity is more isolated from space weather than some have proposed, and we understand better the limits of external influences on tectonic processes. Either way we learn, there's something profoundly moving about the human drive to understand these connections. We're pattern-seeking creatures who look at the world and ask why and how. We see earthquakes and wonder what causes them. We see the sun and wonder how it affects us. And some of us people like Rudolf Wolff in 1853, like the Italian researchers in 2020, like you watching this video, push past the obvious answers and ask the deeper questions about hidden connections and subtle influences. This curiosity has driven every major advance in human knowledge. It led ancient astronomers to map the heavens, Renaissance scientists to overturn geocentric cosmology, modern physicists to discover quantum mechanics and relativity. And it continues today, driving researchers to spend careers analyzing data, debating interpretations, testing hypotheses, gradually pushing back the boundary between known and unknown. Think about the journey we've taken in this video. We started with a Swiss astronomer in 1853 noticing a pattern. We've traced that observation through 170 years of investigation through grand solar minima, when the sun fell silent through the space age, when satellites first monitored the solar wind, through statistical studies that found strong correlations, through skeptical analyses that found none, through theoretical work, proposing physical mechanisms, through debates about methods and interpretation. And we arrive here at a question that remains open, a phenomenon that might be real or might be illusion, a story that's still being written. This is what scientific investigation looks like at the frontier. Not neat, not certain, not resolved, messy, contentious, filled with conflicting evidence and honest disagreement among smart people looking at the same data and reaching different conclusions. And it's beautiful precisely because it's unfinished. The investigation continues, new data accumulates, understanding evolves, the story isn't over. What we can say with certainty is that we live on a remarkable planet nestled in the habitable zone of a dynamic star protected by a magnetic field generated in our core, connected to our sun and to the wider cosmos through chains of physical causation that we're only beginning to understand. The ground beneath our feet, the air we breathe, the magnetic field shielding us from radiation, the climate that sustains life, all of these are influenced by our place in the solar system and by the activity of our star. Whether or not the sun triggers earthquakes, it undeniably shapes our world in countless ways. And recognizing those connections, understanding how we're woven into the fabric of the solar system, might be the deepest lesson of all. We're not separate from space, we're part of it. Every particle in our bodies was forged in stars. Every breath we take depends on energy from the sun. Every moment we exist is possible only because of countless cosmic coincidences and connections stretching back to the beginning of the universe. The question of whether solar wind can trigger earthquakes is in this context just one small thread in an infinitely complex tapestry. but it's a thread worth tracing because every thread we understand brings us closer to comprehending the whole. And there's something deeply comforting in that, the recognition that we're a part of something larger, connected to the cosmos, in ways both obvious and hidden, both ancient and newly discovered. Thank you for joining me on this exploration through time and space, through data and debate, through solar storms and seismic shudders. I hope you'll carry with you not just facts about proton density and piezoelectric effects, but a deeper sense of wonder about the hidden connections that bind our world, about the subtle ways that Earth and Sun dance together through space, about the beauty of questions that remain unanswered and investigations that continue. If this journey has sparked your curiosity, if it's made you look at the sun a little differently, or feel the ground beneath your feet with new awareness, then we've accomplished something beautiful together. The universe is full of mysteries waiting to be explored, full of questions that haven't been asked, yet full of connections we haven't discovered. And I can't wait to explore them with you in our next story here on Sleepy Science. Until then, may your nights be filled with peaceful rest and your dreams touched by starlight. Thank you for watching, and I'll see you in our next cosmic adventure.